All right, welcome back. This is mini lesson number 4 about the hydrogen atom. I hope you enjoyed the web app activity. It's one of my favorite web apps actually for quantum, so I really appreciate that one. I hope you did too. So as we talk about the hydrogen atom, one thing that we need to think about is the quantum numbers. So since we have 3 degrees of freedom, as we said before, we have 3 quantum numbers. And maybe you remember these, maybe you remember 4 from Gen Chem, but we're going to talk about 3 right now. The 4th one will come later. So N is the principal quantum number, and it represents distance from the nucleus. And as you might remember, it has allowed values of integers starting at 1. So 1, 2, 3, they must be positive. L is the angular momentum quantum number, and it represents orbital shape. If we're thinking visually, sort of the graphs from the web app, right? It represented shape. And L has allowed values of 0, 1, 2, all the way up to n minus 1. So L actually starts at n at 0, but it must always be less than n. And the last quantum number is m, which is the magnetic quantum number, and this represents the orbital orientation, or which direction the orbital is facing. And m has allowed values of 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So let's talk a little bit more about this magnetic quantum number. So maybe you remember angular momentum from physics, maybe you don't. But we're going to talk a little bit more about this magnetic quantum number, because it's kind of strange. So the magnetic quantum number m is related to what's called the azimuthal angular momentum, which is represented by this operator LZ hat. And LZ hat is minus imaginary number times h hat times the first partial derivative with respect to phi. So azimuthal, maybe you've heard this word before. I have never heard this word before I took quantum for the first time. Azimuthal is going to be things that are related to the vertical axis, or in our case, the z-axis. So azimuthal means related to the z-axis. So let's apply our operator to our wave function to get some idea of where this magnetic quantum number actually comes from. So what part of the wave function contains any dependence on phi? The exponential term, right? So that exponential part, that e to the I m phi, is actually the only place where phi appears in our hydrogen atom wave functions. So let's just apply that part, because the rest of it won't be affected by the partial derivative with respect to phi. It'll just be treated as a constant. So if we apply negative IH bar, partial derivative with respect to phi, to just the exponential term I e to the I m phi, we'll end up getting negative I squared, which I is just square root of negative 1, so I squared is negative 1, so we have negative 1, or positive 1, m h bar, and then we get our exponential back, because when we take the derivative of an exponential, we always get the exponential back. And so that part will go back to the wave function. If we're thinking of continuing and using the rest of the wave function, that would be an eigenfunction. And this negative I squared mh bar, which is really just mh bar, because negative I squared is just 1, is our eigenvalue. So actually m is the eigenvalue. It comes directly from applying the azimuthal angular momentum operator to the wave function for the hydrogen atom, any wave function. So that always comes out as that eigenvalue. And so let's actually draw a few of these. I'm going to speed up the drawing speed here. All right, so I have 3 axes because we're going to draw 3. But the first wave function is psi 210. So n for all of these is going to be 2 for this, and L is going to be 1. So we're thinking about p orbitals, the 2p orbitals. And in this case, we're plotting when m is 0. So when m is 0, this is the direction when the p orbital is along the z-axis. And it turns out that m is related to the projection from the z, or the azimuthal axes, onto the y-plane, minus the projection onto the x-plane. And if we think about that for this p orbital that I've just drawn, this is like a round-ish shape, right? A dumbbell kind of shape or peanut kind of shape that is along the z-axis. So the projection in y is exactly and perfectly equal to the projection on x. So if we do that subtraction, we get 0. Remember, projections are like shadows. The shadow that gets projected of the function. And so 0 here, in this case, is actually, m. That's our lovely, lovely magnetic quantum number. Comes directly from that projection, right? So let's do this now for the next one. So here, the p orbital is actually along the y-axis. This represents 2, 1, 1. So psi 2, 1, 1. L here is equal, or n is equal to 1, positive 1. And so if we think about the projection on y, there's the full projection on y, or 1, because the orbital actually lies along that axis. But the projection along x from the z direction is 0, because nothing lies along the x-axis. And so our projection of y minus our projection of x gives us 1. And so our m value is 1. And so the last one we plot should be along the x-axis. And I'm really bad at drawing this. This is coming in and out of the plane. This is along the x-axis. So this would be psi 2, 1, negative 1. And this is because if we look at the projection on y, it's 0. But the projection on x, where the orbital actually lies, is 1. It's 100% along the x-axis. And so that projection is going to be 0 minus 1, or negative 1. So this is where m actually comes from. If you've wondered what this mysterious magnetic quantum number was in Gen Chem, now you know that's where it comes from. Okay, so now let's also look at the energy levels for the hydrogen atom. So keep in mind here that Bohr was correct only for the hydrogen atom, not for anything else, but the Bohr model is actually perfectly correct for hydrogen. So if you remember back to your Bohr model, or the Rydberg equation, energy depends entirely on one quantum number, and that's n. So E is always written here as a function of n for the hydrogen atom. We get negative E squared, where E here is the charge of an electron, over 8 pi epsilon naught, which is our permittivity of free space, A naught, which remember was our Bohr radius, n squared. So n is our quantum number, and the only quantum number that comes into play here. And so we get sort of our cute little Bohr orbits or Bohr orbital model here, where our energy depends on which orbit we're in or how far the electron is found from the nucleus. So what is the degeneracy of a Bohr model? So let's think through this a little bit. I'm not going to give you the answer. I'm going to make you think through this one. So if we think about n equals 1, the only possible combination for n equals 1 is L equals 0, m equals 0. So we have one level here. So we're going to switch pen colors to something fun. We'll go with purple. So we have 1 here. If we go to the next one where n equals 2, we get L equals 0, m equals 0, which is our 2s orbital. We get L equals 1, m equals 0, m equals 0 or plus 1 or minus 1, which is our 3 2p orbitals. So now instead of just having 1, we have 4. How many would we have if we went to n equals 3? How about n equals 4? Can you find a mathematical relationship? If so, leave so on the Slack discussion. I'd love to hear about it. So that's my challenge to you, right? Find the rule for degeneracy here. All right, and one last thing before we close out our hydrogen atom is the Zeeman effect, because this is going to come into play again when we talk more about spectroscopy. So the Zeeman effect, you may or may not have heard of this before. If not, great, I get to be the first to introduce you to it. All right. So if we plot our energy, so here, remember, everything is degenerate, so we're just going to draw our 2p orbitals. So we have 3 2p orbitals. Their L values are all the same, their N values are all the same, but their M quantum numbers are all 3 different. And in the absence of a magnetic field, they're perfectly degenerate. They all have the exact same energy. But as soon as we introduce a magnetic field, they split, where the M equals 0 stays exactly at the same energy it was originally, but m equals 1 goes up in energy, and m equals minus 1 goes down in energy. So what we find here with the Zeeman effect is that magnetic fields have the ability to split energy levels based on the m, or magnetic, quantum number. Curious. So we'll come back to this a little later, towards the end of term when we talk about spectroscopy. The Zeeman effect will come back up when we talk about EPR specifically. All right, stay tuned for more fun things this week.